How you guys doing? You guys are all super relaxed. You got your exam out of the way.
Next week.
One exam down. At least one to go for integrated. All right, so everyone remembers we have our exam next Friday, a week from tomorrow. Fantastic time. It's right in that great time slot when like you don't really have anything else going on, 5 to 7 p.m. Can I, let me hijack this. So remember what you clicked in for this. I'd like to know, and I'm not going to bring this back to you. All right, click in your answer to the question I have up there with my own scribble. Are you going to vote November 8th?
I mean, I'm going to vote for
So, I'm really hoping that you guys know what's happening on November 8th.
We don't have class that day.
We do not. Why do we not have class that day?
They want us to make good civil service and go vote.
Is that for real?
That's great.
Is that real? You guys, 29 of you guys are going to vote?
I didn't vote in the clicker, but I plan on voting.
All right, so the next question, let me ask one more question along these lines. I want to know, registered to vote. Son of a...
What if I registered but I haven't gotten the confirmation not have been?
If you tried to register to vote, I want to know, A, yes, B, no. All right, everyone clicked in. Give me their feedback. Brianna?
I got it.
Okay. Do you guys know, for the quarter people who didn't, do you know how to register to vote? Would it be useful to have someone to come to a class next week sometime to give you some feedback, some info on how to register? It would be right before or right after class. It's not going to be during class, Demetrius. I don't know if that's what that smirk is for on your face. We're not going to give up class time, so. All right, so there's a student organization that's heavily involved in climate change. They want to teach renewable energy and environmental sustainability. TREES is the name of the group. And for the fall, their big project that they want to do around climate change is they want to make sure at least, regardless of which way you're going to vote, that you register to vote and that you know something about the candidate. So they're going to hold some sort of drive where they're talking about the candidates, their stances, specifically about climate change, but they're also going to help you figure out how to vote. So I'm going to try to bring someone in from that group next week so that you guys can get an idea if you don't already know how to register, because that's one of the biggest barriers for first-time voters. All right. Monday night, you guys know what's happening Monday night?
Yeah.
What's happening Monday night?
Presidential debate.
First debate, 9 o'clock. If you guys want to know about the candidates, watch it. All right, let's go back to this question that we had here. Yeah. Wish Bernie had gotten further.
This is the same. There's also this is the same one, right?
I believe so.
Next week, Tuesday, Thursday? Awesome. So Miana just said that next week, Tuesday and Thursday, there's a voter registration drive in Trabant. 12 to 3? Fantastic. Thanks for bringing that up. So the other student group is trying to plug into it, but it seems like that's a really good way to start. All right, so let's go back to this question. So in class, we're going to be talking a little bit of a deviation today, but it still applies to solvents and solutes. Increasing temperature tends to increase the solubility of ionic compounds in water. Have you guys seen that? Where have you seen that increasing the temperature helps dissolve things? Morgan? Yeah, so if you put a tea bag in cold water, you're not going to get much dissolving. So that's organic molecules as well as salts. So things just dissolve better when it's warm. We're all comfortable with that. So then the statement here is, likewise, increasing the temperature increases the solubility of gases in a liquid like water. So what do you guys think? Everyone clicked in their answers on this? We only have 23 responses, so I'm guessing no. So make sure you clicked in. Is there really only 32 of you guys here? Fail. All right. So we have no idea. So let's take a look at some data. Talk to your neighbor. Try to see what does this data tell us.
I remember some about that in organic.
I don't think gas is actually.
So, simply looking at the graph, what does this data tell us, Alex? Solubility of gases goes down. It's important we say gases because solutes is not the same. It's the opposite trend for the most part. So as we raise the temperature, the solubility goes down. Is it just a little bit of a change? How do you know that, Javante? Well, it looks like a bit of an exponential graph. What does it start out as, and what does it end? What's the relative change over the course of this temperature range? Does it go down by 5%, 10%? How big of a change is it? Jose? Does everybody agree? So how do we look at this and say how much the solubility goes down? So it starts at about that line, right? Goes down to what at 60 degrees Celsius? Goes down to somewhere in this range, right? So it goes from 0.34 down to 0.8, 0.08. How big of a change is that? It's huge, right? It goes down not by 100%, which would be, I guess 100% is a bad way to say it. It decreases by like fourfold. 4 times less is soluble at a higher temperature. So it's a really significant effect. So I want you guys talking about why. And here's a graph for a number of different compounds. Gases dissolving in water. So you know it's not just one compound. Talk amongst your group, and I want you to try to figure out how you can describe, with your knowledge of what molecules do at different temperatures, why it is that gas solubility decreases with increasing temperature. Try to come up with some justifications, some reasons why. What do you guys think? It's not about getting it. It's about having an idea, having some way to explain. So get it with a K. Dana, you're paying more attention.
Molecules attached. It's a separate molecule attached.
So what's happening in the molecules when you warm them up? Are they?
Kind of like it's
So think about in water, when we warm water up, do those molecules get further apart?
kind of combining.
Okay. So what does that mean about the gas?
How do I explain it properly?
So I want you guys having a productive conversation, not saying I don't know. Brooke, what are your thoughts?
We didn't really
Okay.
Well, like we said that when when you're increasing the temperature, they're like moving faster, the particles. But we didn't really
Okay, so that's a good start. So it means that when we're thinking about this, molecules we start to think of as particles. That they're bonded together covalently, so when they heat up, they're going to be moving faster. And the liquid, when it heats up, is it spreading out? So water, when you warm it up from 10 degrees to 30 degrees Celsius, moves apart. Is that right? No. What does it do? just moves faster within the same volume, right? We're not expanding to a gas. We're not doing that until we get boiling, or at least a small part of them at the surface might, but overall the solution doesn't boil. So those particles are moving faster, which means we have more kinetic energy. And if you think about having more kinetic energy, what holds these gases in solution? Why do some of them, why are they dissolved? What has to happen in order for something to dissolve? Demetrius?
Disassociate from each other, and then it's a solution.
Disassociate, what's dissociating?
The solvent in the solid has to disassociate in the solid.
So you're thinking more of salts, right? So gases start as separate, and then they're going into solution. Taylor? So do we have any ions? Great, so the covalent bonds in the gas aren't breaking apart. The covalent bonds in the water aren't breaking apart. We'll get into a little bit of where that might not be the case. That applies later. So then what happens? Why does a gas dissolve? What has to happen for something to dissolve? Shane?
The intermolecular forces of the solvent have to overcome the kinetic energy of the gas.
Yeah, so if a gas dissolves, it means it has to have some interaction with the solvent. It might be really minimal. What kind of interaction do you think helium has with water? What kinds of intermolecular forces, Jose?
I was thinking the hydrogen bond.
So in order to have a hydrogen bond, it has to either have a hydrogen or electronegative oxygen with a lone pair, nitrogen, fluorine. Cosme?
I thought it didn't have an interaction because it's a noble gas.
So it doesn't have, most of the types, it doesn't have a dipole. What kind of interaction does it have? Javante? Just dispersion forces. That's why that one is so poorly soluble compared to the other ones, even at a low temperature. The ones that are a bit more polar or heavier will have more solubility. So there's some interaction. It's a weak interaction, right? They don't dissolve nearly as much as salts or as other solvents, but they do dissolve a little bit. And as we heat it up, we speed them up, and now that force that holds them, that minimal interaction, decreases, and then they can overcome, and that makes them less soluble. Jace?
The O2 and the CH4, why the O2 was below the CH4.
So there's a bit more to it than what I just talked about. So dispersion forces, the surface area of a molecule also plays a role. And CH4, because it's tetrahedral, has more surface area, which means more dispersion forces can occur. Good question. Sabrina?
I don't, this is just kind of like force, but like, I don't understand the difference of like disassociation versus like just one force overcoming another. Like, what is the difference between those two things?
So disassociation means that you have two things that were typically ionic bonded together, and that for some reason now they are separate. So they disassociate from each other. Usually that's something solvating it, water solvating. Versus intermolecular forces are two things that have a small interaction, and that when that small interaction, it's not a full charge. That's the big difference, I guess. So we can talk about this more after class. I think that's a really good question that we should get into, but not in front of the whole class. So then let's talk about, we've been building this molecular view of the world, of liquids, and of gases to some extent, which we'll be doing a lot more of next week. If you look at this image here, what we're trying to depict is that the gas molecules, we actually drew them out as particles. They're moving around. We've been talking about, you can see them moving around, and pressure is how frequently they collide with the outside container and how heavy they are. Changes with how fast they go. But some of them dissolve, and it shows that with the spheres that are in the liquid. So what's going to happen as we increase the pressure? We're going to push down on the top of the cylinder. We're going to decrease the volume. The number of particles stays the same. So what's going to happen to the solubility of that gas in the solution? And you assume that there's no temperature change here. Oh. Assume we're not changing temperature. What's going to happen to the solubility of the gas once we increase the pressure? Now I want you to think about why. If you're not comfortable explaining it, make sure you talk to your neighbor.
explanation of why.
Okay. McKenna, can you share your thoughts? What's going to happen when we increase the pressure?
You said increase
Okay, you want to go ahead and do an explanation there?
because when you're pushing it down, it's like creating, it's the more pressure and it's creating the particles to like be closer together.
Okay. So if the particles are closer together in the gas, then why is that going to increase the amount that dissolve in the water? Don?
This is going to sound stupid, but I learned that it was because there's less volume, so less volume, so there's less room for them to go. They have to go. Like how they follow.
So I don't know if I call that stupid at all. I think that if you force those same number of gas particles to be in a smaller volume, maybe the more technical way is to say, well, there's going to be more collisions with the surface, and those collisions result in some of them being dissolved. So that trend holds true for a ton of different gases at different pressures. So this idea of us thinking about if we envision all gases, liquids, and solids being composed of particles, and how do those particles act based on what they're composed of, what intermolecular force is based on the shape, how heavy they are, and what types of bonds, we can make predictions like this that really get us pretty far. And I think on this question, before we even had people responding, we had about 85% that were good with this.
Is each one of those lines a different gas?
Each one of those lines is a different, what are those different lines? Gram, Newton meter, cubed.
You have no idea what it is.
Pressure versus dissolved. Not sure. I just had an assumption in my head of what it was, that it was different gases or different temperatures, but I'm not quite sure.
Isn't that in Pascal's?
Dissolved into
So it's
different weights.
ozone. I don't know. I'll come back to you guys, let you know actually what that graph is. I apologize. So let's take them. That's actually a really good segue, right? Because what the hell is that? Let's talk about something that actually matters. Does that sound good? You like that transition? Okay. I want you guys to look at this pie chart. Does anyone watch How I Met Your Mother? Gotta love pie charts. All right. Take a look at this graph, and then there's a question on your handout. It says, what CO2 sources on this slide, are humans mostly responsible for, and which are mostly naturally occurring? So think about the carbon cycle. This is saying, where does carbon CO2 come from? We're also going to talk about sinks of where it goes. I want you to write down the sources that humans are involved in and which ones we're not. Have you seen my toy? Have you seen my toy? I can write on here. It's very fun.
Yeah.
It's nice. Helps interact with class.
So, like, how much? Okay, so how much would this 38 be of human respiration?
Circle what you think is appropriate for humans.
Okay, well, I definitely think these two are. But whatever percentage of respiration that humans
So circle what percentage you think it might be.
now, how much?
Dude, I'm holding a gun to your head. You have to choose. Circle some part of it.
All right, so I'm gonna say that. Wait, I gotta circle it.
You gotta circle a part of it. Come on, do it. No.
Circle a
down.
part of it, like that
Yeah,
much.
don't.
I don't know.
All right, Brian, what'd you circle and why?
And then,
Taylor. Sorry, Brian, go ahead.
alright, fossil fuels, deforestation, and a partial amount of the respiration.
So this is a really good question. When we talk about humans' influence on the world as far as climate change goes, if we ask a regular person on the street how, if they understand that CO2 is involved in this, a lot of times we'll get that respiration is one of the biggest ways that we contribute to climate change. What do you guys think about that? Talk amongst your group. I want you to decide how much of respiration you think comes from human activity. how much of that respiration CO2 being produced comes from human activity?
One species versus every other
Claudia, how much do you think? What do you guys think?
as much as it says up there, because we are overpopulated, but like not to that extent.
Okay, so the question is, when we breathe on a regular basis, we breathe out some carbon dioxide. So am I solving global warming? By holding my breath. So I don't have the exact numbers, and I'd love it if someone wanted to look these up and post to Canvas discussions, but my understanding is that it's less than a fraction of 1% of that. It's basically insignificant. Where do we contribute the most to CO2?
Isn't it on the surface of the ocean too?
So we do a huge amount through burning of fossil fuels. I didn't realize cement production was such a big one. I'll have to look into that more. But I'm imagining calcium carbonate, pulling that out and then having that react will release some CO2. Deforestation, changes of land use. And then the other part that we want to look at, those man-made ones are mostly the ones at the top, is what are the sinks for CO2? What is it that pulls CO2 back down? And the major ones that we talk about right away are?
Sorry, what exactly is surface ocean? Because like when I think of surface ocean, I'm just thinking of like a bunch of crap floating in the ocean.
Interesting. So,
Like stuff like on the surface.
going back to the slide that we just had with that picture of gas above the liquid, why are we only talking about the surface of the oceans?
Because the CO2 can't go up after a certain atmosphere.
Okay, so if you have an interface between a liquid and a gas, that the CO2 will dissolve, and it'll dissolve a certain amount, but then it diffuses into the rest. But it doesn't really get all the way down. So there's huge chunks of the ocean where there's very little CO2 dissolved because it doesn't diffuse as much. So here what we're talking about is where's the flux, where's the change, what pulls it in, and what releases it back out. So that's a good question. So the main things that pull it down are photosynthesis and the oceans. So I want you guys to talk in your group. How does us increasing atmospheric CO2, are you guys all convinced that atmospheric CO2 is going up? We can bring up NASA's page, right? We're at 403 parts per million now, over the 300 that has ever been achieved. So we're at 400 and something, right? So that's going up. The partial pressure, the amount of CO2 in the atmosphere is going up. So is the amount of CO2 that's dissolved in the oceans going up or going down? And I want you to talk in your group to decide whether you think that the surface oceans has more CO2 going into it or less. Is that the only factor? Are there any other factors that would influence dissolving gas? Yes, bro. So it's where the gas particles interact with water, that's where the most dissolving is going to happen. And then somewhat diffuses down, that top is where most of the dissolved gases are. So Michelle, you want to describe your thoughts?
We were thinking that since one of the more carbon dioxide into the atmosphere is more concentrated, so there's more, it's like there's more molecules making it more dense, so it will force some of them into the
So, like what Dawn was talking about, that if we have more gas particles above the surface, then more of them are likely to dissolve and go into the ocean. Great. Is that the only thing to consider? Okay.
I was talking about how global warming and the temperature of the earth is increasing.
So how is that related to CO2?
So we stated in the beginning of class, as heat increases, the solubility of the gas will decrease.
So we release more CO2 in the atmosphere, and part of it makes it dissolve more in the liquid. But at the same time, we know that CO2 traps in heat, and that heat changes the solubility of gases. So I want you guys to look at this very complex diagram that we have next. So these are, you already know about these. So here's a figure with a lot of information in it. I want you guys to look at this and determine what information can you conclude. What's the overall outcome of all of this related to the oceans and the atmosphere? And I believe there's a guiding question or two on your handout worksheet for this.
So would it eventually balance out?
That's the question.
So we're making it less solid, but at the same time, the temperature is going up. The question is the temperature going up enough to matter?
No, it's less soluble. It's just like
Oh, so the temperature, yeah, the temperature's going up, lower solubility. The atmosphere is also going down, lower.
So, can I hear from Alex? Let's start out here. What are the colors telling us? What information are we getting out of the colors? You want to pass for now, Alex?
Oh, what's the colors? It's like the recent changes versus the pre-industrial changes.
Pre-industrial, what does that mean?
Like Bruce.
Okay, Tom's going to answer that? So what was it like before the Industrial Revolution? What did this tell us about before the Industrial Revolution? Great. Why did you say it's more balanced before the Industrial Revolution?
It just shows that, well, the green arrows, it shows that, I guess the amount of CO2, the same amount that goes in is the same amount that's rising up.
Is that true in both land and over water? Where do we see land? Where do we see water?
Land.
So it's a little bit easier to see on the LCD displays instead of the front and back screen. But the left side is on land, the right side is on over water. And before the Industrial Revolution, there was a relatively balanced amount of CO2 being released by respiration, taken up by photosynthesis, released and absorbed from the oceans. What about since that time? What do the red arrows tell us? Chelsea?
Well, I was going to say how, about the industry, after the Industrial Revolution, how with industry, everything, all the products are, exponentially, multiplied. So then obviously you have larger green arrows to show that magnification.
So I don't know that the total photosynthesis or respiration numbers change. That's still the biggest impact. I think that's one of the most important things when you look at this, is it's compared to what's naturally occurring in both directions, we're relatively small. But what conclusions can we say about our impact? Javante?
Well, you can see at the right, on the left for land, there's a lot more CO2 being taken out of the earth. And then on the right, you can see that the CO2 that is coming out of the earth, there's more blowing in from the
So what's going into the ocean? CO2. So we warm the Earth up, gases dissolve less. But we have a higher partial pressure, gases dissolve more. Which one wins in that case? Which is more influential? Pressure turns out to be more influential because there's more dissolving now than being released. What's the net effect on the atmospheric CO2 though? 15 what? Where? Everyone see that on the right side here? If you add up all the things that are getting pulled down, all the things that are getting released, we are having a net impact of increasing by 15 ppm, and I think that's, I don't know the time scale on that.
58 to 2004.
So that's over about 50 years. Okay, cool. So the oceans help out. They're sucking out some of the CO2. That's a good thing, right? What happens when CO2 dissolves in water?
Doesn't it ruin the levels of calcium carbonate and destroy the reefs?
So CO2 gas has a physical equilibrium that gets applause. It's an intense ringer, right?
Now my Pandora just randomly played.
I'm game. You ready? You got a spot right here in the middle. Get up. Okay. CO2 dissolves in water, right? What happens when CO2 dissolves in water? How does water become acidic?
The donor, isn't it like the conjugate acid?
So first there's a chemical reaction. CO2 plus water, what does that yield? Does anyone know? Carbonic acid. H2CO3. Carbonic acid sits in water for a while. What happens to that molecule? Can anyone draw out the Lewis structure for that? Go ahead and draw the Lewis structure for carbonic acid. Okay, you're almost there. What are you missing?
H's.
So check with your group.
Oh, is there a spot?
By Lewis structure, that means to draw everything out. Don't just draw a polyatomic ion as one chunk of the sound.
That makes any sense.
Where's the Lewis structure?
I started
Lewis
it.
structure,
I
come on.
started it, but it's wrong.
I'm not seeing your Lewis structures, guys.
Sorry.
What's yours?
I think that's it.
Oh, you're just hiding it.
Yes, no,
Make sure you have the right number of atoms there, buddy.
I think.
All right, so just a little foreshadowing. This is important to be able to draw the Lewis structure of a molecule, okay? A little foreshadowing. You should be able to draw the Lewis structure of polyatomic ions. And that polyatomic ions happen to have protons attached to them instead of sodiums. You should still be able to draw that. So what polyatomic ion is hidden within this molecule? So we should recognize that there's CO3, but instead of 2 minus, we have 2 H's that are H pluses. So to draw a Lewis structure, we would draw a carbonate, and then we would draw H, carbonic acid. What do you guys know about carboxylic acids? Hopefully we recognize carboxylic acids in this molecule. What happens to carboxylic acids when they're in water? Say again? Okay, so they can't hydrogen bond, yes. And what else happens to them a small percentage of the time? I'll give you a hint. It's in the name. They act as an acid, which means
They protonate.
they deprotonate. They give up a proton. So these OH bonds are long. They're weak. Water can solvate those. It only separates about 3% of the time. We'll talk about that a lot in equilibrium when we get there. But that means that this molecule, carbonic acid, can release 2 acidic protons. So if I go up here and draw equilibrium, what we end up getting is H plus aqueous and HCO3 minus aqueous. That means that one of those protons was released to water, and we end up with bicarbonate. But then that's also an acid, and we can also have carbonate, and then we have another proton that's released again. So when CO2 dissolves in water, it's not good. What happens to the pH of water when CO2 dissolves? So pH is inverse to the concentration of H+, so the more H+, the lower the pH. Means more H+ is in water, it's more acidic. Just means that it's cleaner, more H+. Why does that matter? Why do you even care if there's more H+ in ocean water?
Because of like coral on certain plants and animals that have a certain number of like concentration of water to survive.
So they need, coral is made of a lot of things, but calcium carbonate is the main component. Calcium carbonate is a base. When you have a base coming in contact with protons, then you have this dissolving, which means coral dissolves, which changes reefs, which changes ecosystems, which does a whole bunch of other things. So there's kind of the big picture. So what I wanted to get into here, because you're going to be using it in your biology class in a couple weeks, is that gases, when they dissolve in our lungs or over the ocean, we have to think about how the partial pressure, or how much of the gas is composed of each component, and how that affects things that have dissolved. Taylor?
So I heard that the ocean water was increasing, the temperature was increasing. Is that because of the CO2, or just because of the global warming? Like, is the Earth getting warmer?
Yes. So why is the temperature of the ocean going up? Because there's CO2 is a greenhouse gas around the planet. Traps heat from leaving our planet. That means the air warms up. If the air is warmer, what's going to happen to the water? Water warms up too. All right, so the last little thing on gases before we go back to some calculations for colligative properties is this term partial pressure. Partial pressure sounds complicated, but I don't think it is, and I hope that this visual will help. So if you were to take a scoop of air at atmospheric pressure, which is here at sea level basically, you're going to find, if you pick apart all the molecules and you count them, 78% of those molecules are going to be N2. 20 or 21% are going to be oxygen molecules. And then we have a little bit of argon, carbon dioxide, and some other stuff in there. So, 2 ways that we can increase the amount of gas that dissolves in a liquid. One is we squeeze it, right? We compress it and we increase the pressure. That means we're going to have more particles, more frequently getting into the liquid and staying there. What's the other way that we can increase, without increasing pressure, the total pressure, how can we increase the amount of gas that dissolves in a liquid? Think about that for a second. Talk to your group. Without increasing the total pressure, how can we increase the amount of gas that dissolves in a liquid?
Based on that graph that we saw before.
So Katie, can you share your thoughts with us? Okay, we could change the temperature. Would we increase or decrease it to increase the amount of gas that dissolves? So So if we make it colder, more gas is going to dissolve. Great. What's another way? Thomas? So if we just decrease the volume, but the pressure stays the same, then that doesn't have any effect. So we're saying the pressure doesn't change. What's one other way? We just talked about it.
You could increase the volume.
So changing the volume shouldn't make a difference. So we're talking about over a glass of water, we make it a larger column or a smaller column of air. It's not going to matter. Taylor, what are your thoughts? The amount. What do you mean amount? So what if we change the partial pressure of each? So what if carbon dioxide, instead of being 0.04% of the atmosphere, what if it was up to 0.05%, 0.0005? If we increase the partial pressure of CO2, that's the same thing as increasing the total pressure of the whole thing. The total pressure, but if the makeup of that gas shifts to be now more CO2 than other things, so maybe there's less O2, there's more CO2, then that partial pressure, the fraction of the total that is one gas, then that's going to affect how much dissolves as well. That's what we're doing, right? In our planet, we're not changing atmospheric pressure. We're making more of the gas, CO2. We're increasing it from about 300 parts per million to 400 parts per million. So we increased it by 33%. It's a huge difference when we're talking about how much is going to dissolve in the oceans. All right. There is a law for this. It's called Henry's Law. It basically says that the concentration of gases that dissolve is directly proportional to that partial pressure of the gas above. If you change the temperature, this relationship changes. But you guys don't have to scribble down this equation. I don't know that that's nearly so important. But for any gas, you have a Henry's constant. The constant just tells you, well, for every 0.1 atmospheres, this is how much gas will dissolve. It just is that amount, that fraction of it that will dissolve. But really, the key relationship here is that there's a direct proportionality between how much the partial pressure is of the gas and how much dissolves in the solution. And that's what's going to be important when we start talking about respiration and having gases dissolve in our blood and released from our blood as well. And if we're in a packaging plant for Coca-Cola, how do they get so much CO2 into our drinks? They have a huge partial pressure of CO2 over the top of it, and then a lot of it dissolves into the can. So simple variant of that. All right, so let's move back to colligative properties. I want you guys thinking about stuff dissolving, so we're going to go back to, I think these are the last couple of questions on, are these on the handout from today, the worksheet from today? We're going to mix back and forth. Okay, so which one of these here shows a solution that is hypertonic? The solution, remember, being hypertonic compared to the cell. All right, closing out. Dan, what does hyper mean? More. What's another way to say hyper? What do you think when you hear hyper? Is that what you think? That's what I think of. Right. So hyper means more. It means greater. So I think that hyper and hypotonic can be terms that a lot of times I even early on had no idea what the hell it meant. I was like comparing the two. I was like, what side? I thought it was like a certain ratio. It's really just saying that which one is greater in concentration than the other one. So in this case, A is by far the greater concentration compared to the cell. So it's always relative. It's saying this one is greater than that one. And here's some definitions that I'll put up later. ISO just means the same. So you can look those up afterwards. That's why I put them there, if you really need the definitions. So we're going to be working a little bit with some different forms of concentration today, talking about osmolarity and osmotic pressure in the rest of class. And we're going to talk about how to find molar mass from some of these things. So at the end of last class, it was really quick, really fast, but I said that osmotic pressure is derived from the ideal gas law. Ideal gas law, you guys will see some next week. I really don't want you to do a lot of calculations with this, but I want you to be able to look at the world about the molecules of gas and how they interact with each other. What happens if we increase the number of them? What happens if we warm them up? What happens if we change the space that they take up, or just increase the pressure? So PV equals nRT is ideal gas law. And osmotic pressure is really closely related to this. So if we rearrange this equation, is everyone okay with this rearrangement? We say that divide both sides by volume. So on the left side we have pressure, which is going to be akin to our osmotic pressure. And so in osmotic pressure we call it pi. It's a little bit different than regular gas pressure. And then what units do we typically have for molarity? Val, what are the units of molarity?
Moles per liter.
Does anyone see those units hidden on the right side of this equation? Okay, so N is the moles, V is the volume, can be liters if we use the right units. So basically what this becomes, pi, osmotic pressure, is equal to the molarity of the solute times the gas constant R times temperature T. There's one additional caveat though. We're talking about colligative properties. What are we missing? Van Hoff factor. So that means if something dissolves and it becomes two particles, it has twice as much of an effect. And our gas constant that we're going to be using for the most part is up here. You might want to take note of that because you're going to use it for calculations coming up. Everybody got it? 0.0821 liter atmospheres per mole Kelvin. And yes, the units are very important. All right, you guys ready? 5, 4, done. Okay, so the one last thing to talk about is if you go into the medical field, you will see osmolarity as a concentration unit. Let's look at a couple different examples. Pure water. 0 osmolarity. Surprise, right? Sucrose. 2 molar sucrose. What's the osmolarity of that solution? Anybody know? Two osmolarity.
Are we talking to room temperature?
Doesn't matter. 2 molar sodium chloride. What's the osmolarity? Everybody agree with 2? I hear 4. Why 4, Javante? So on your paper, I want you to write down how molarity and osmolarity relate to each other. There's a spot for it on the handout for today. I want to see everyone writing out some way that how osmolarity relates to molarity. Write out your relationship.
I'm sorry, my handwriting is terrible.
You can actually set your hand down. It registers with dependence.
Oh, really?
So you can set your hand down and write.
What do you, I'm
Pick this
confused.
up.
Oh.
Write like normal. Pretend it's a piece of paper.
Okay.
just
What?
saying that like a lot of people do this when they're writing.
Oh,
You can
okay.
actually put your hand down because the pencil. So how did you figure that out?
Just by the relationship here.
So why would it be molarity times the Van Hoff factor?
Because, osmolarity, and then for sodium chloride, it has a Van Hoff factor of 2, so you'd multiply the molarity by 2.
So why do we care? Why would we want to have a concentration unit that includes a Van Hoff factor? So let's say you're in medicine, you're out in the field, you're giving someone an IV bag, and you want to know, it says osmolarity on it. Why does that matter? Why is that more important, the osmolarity, than the molarity for an IV bag? Taylor?
Wouldn't the osmolarity tells you like the concentration, and it would be able to tell you how many things are like dissociated into the.
Why does that matter? Why do we care about the number of particles associated in solution?
Because can't they associate with other things once it goes into your body? Like,
Possibly, but not the reason we're so worried. Don?
don't want your blood to aggravate.
So we go back to that hypertonic and the hypotonic definitions, right? It didn't matter what those particles were, but when you add IV to someone's blood, you want to make sure it's isotonic. Otherwise, we're going to burst red blood cells. Because those red blood cells, if there's too much solvent outside, or solute outside of the red blood cells, then the red blood cells are going to shrink. The water is going to leave the red blood cell. If there's less solute outside, then that means the red blood cells are going to fill with water and they're going to burst. So we really don't care what the molarity of the solutions is. We care about the osmolarity to make sure that the number of particles doesn't cause osmosis that lyses our red blood cells and makes us be very, very, very unhealthy. Pretty sure it's really easy to die if you just inject water into your blood, right? Yeah, just water or really, really concentrated, well, air too, yes, for different reasons. But osmotic stuff is actually pretty critical. Okay. So let's have you guys use this to do some calculation. So here's some information. I want you guys to figure out what is the osmotic pressure of this solution. And this is on your worksheet from last class. What was the face for it? Give me a weird face.
Yeah, exactly.
That's a bad idea. You have your worksheet from last class?
Oh, is this all?
Yeah, the rest of the questions are on the worksheet from last class.
What are the chances you have an extra one of those?
None. That's why I sent out an announcement last night to bring it.
I can't find it.
Fail. So the rest of the class is going to be doing calculations, so if you're welcome to stay. But hopefully you can use some of what we talked about for the fill up. Well, sometimes I do, sometimes I don't. So because you said that you were interested in it, that's why I wanted to. Say again?
I'll catch up with you tomorrow because our meeting is going to be short.
Okay, sounds good. What is this?
Temperature?
A little bit more.
What do you mean?
I need you to explain when you say things. You give me really short answers. I need you to give me more full explanations. So what is this with temperature?
We're adding the constant plus
In order to do what?
temperature. The Kelvin?
Okay, in order to go from Celsius to Kelvin, we need to add 273.
Right.
So, add your units and add all of your units here.
Okay.
Raise your hand if you need some help moving in the right direction.
No, we need letters.
No, I know how.
I don't have a calculator.
I only found out before this exam. Oh, it's,
You would have,
isn't it like polarity is per liter? So it's,
And then it's this question. 2
So is another 45 seconds going to be enough?
no.
Is it going to be enough for those who have their calculator and are doing it with their own calculator?
I felt that she.
I have a baby calculator.
That is awesome. Is that what you're going to use on the exam?
That's what I did last year.
You can use a graphic calculator if you want. Do whatever you're comfortable with. Make sure you practice.
My graphic calculator broke. So before one of the exams, I had to go to like the student center and buy this for like $2 to use my exam.
All right, just about everyone's done. And we're pretty sure everyone got the same answer, right? All right, what happened? Okay, is it to do with the Van Hoff factor? Or? All right, so let's do this. So we want to find what? What are we trying to find? Pi. Okay, so we know that that is equal to the Van Hoff factor. What is it for KCl? 2 times molarity. What's the molarity? .0500. Sorry.
0.751 liters.
It's 751 liters of solution, right? Of water. So I guess we would assume that that should be of solution if it's to be very accurate. And then what's R? 0.0821
liters atmosphere per moles of Kelvin.
And the last thing we multiply by 23, right?
But we have to convert it to Kelvin.
Did anybody use 23? So here we have to put in temperature, which is 273.15 plus 23.0, and that's in Kelvin. Sorry, it's kind of ugly there, right? So Kelvin cancel out, liters cancel out, moles cancel out, and we're left with what unit? Okay, so if we do all these calculations, what do we get?
3.24 atmospheres.
So why did a lot of people answer B?
Forgot to double.
Is that the Van Hoff factor? So did everyone convert to the right temperature scale? Nice, that's usually the biggest error, and that ends up with one of these other answers. So if you guys were given osmolarity, how would you have used that here instead? If you got osmolarity of the solution, how would we use that?
You put it on this side, and then put it equal to
Osmolarity being a concentration unit. Volume?
I was going to say we wouldn't have to include the Van Hoff factor, but I'm not.
So if osmolarity is molarity times the Van Hoff factor, then Alex, how do you use it?
You just multiply it by R and T, so the temperature and constant.
So that is osmolarity. I times molarity. All right, and let's not really talk about that. Have you guys heard of reverse osmosis for water purification? A lot of houses have reverse osmosis. What does that even mean? What's that, Katie? Nice and loud.
Process in which solvent is forced through a semi-permeable membrane using a more concentrated solution.
So it's the exact opposite. It's reversed. Then if you have salt water or something on the outside, and you put a lot of pressure, then that means that pure water is going to flow through the semi-permeable membrane. The more pressure you apply on the outside, the more pure water flows through, until that amount of pressure equalizes the osmotic pressure of the solution. So just another way in which we can use osmosis. All right. So here's another problem that you guys had. So we have a medical researcher analyzing a patient's blood for a mutation in hemoglobin that results in sickle cell-like disease called Bangkok J. This mutation in hemoglobin can be detected by an increase in molar mass of the protein. I want you to determine if this particular sample of blood from this patient has this mutation or not. So they take a certain amount of their hemoglobin, 21.5 milligrams, dissolve it in 1.5 milliliters of water at 5 degrees Celsius. They get this reading for the osmotic pressure. You guys to decide if this is the mutant or if this is the wild type. Go ahead and take a couple minutes, try to figure this out. You have all this on your worksheets from last class. Question?
Well, I know it's a kilo of something.
So let's bring everyone back together. What does that KDA stand for? Salma? What's a kilodalton? What does kilo mean? 1,000. Okay, so it's 1,000 Daltons. You guys are good? What's a Dalton? Who's Dalton? The guy. Dalton's the guy. He's one of the guys that helped us discover parts of the atom. So Dalton is another way of talking about grams per mole. Because you guys are biologists, and that's what biologists do. You guys are confusing. So biologists, when we talk about the mass of a protein, instead of saying grams per mole, it's just easier to say Daltons. It's shorter, so that means these proteins, are they big or small proteins? 63.35 kilodaltons. How big is that? 63.35 times 1,000 grams per mole. 63,000 grams per mole. Is that a heavy molecule?
No.
Compared to sugar that's 180? Yeah. It's a pretty heavy molecule. All right, so figure out which one of these it is. You can look things up if you need.
Yeah, exactly like the problem we're talking about. I still don't understand what it is. Isn't it just pi over I right? That's right. That's what we're going to do. If you're trying to solve for molarity, wouldn't it just be pi over I ocean?
Alright, so let's bring everybody back together. Let's get on the same page. Because I think you guys are not aware of how much you know. So let's start off here. What do we know? Salma? We know the osmotic pressure. Great. Can we just use that directly in the equation? Why can we not use that directly in our equation that we have? It's in a different set of pressure units. So you can either Google what the conversion factor is, or there's another option. You can look up the gas constant in unit of torque. That's fine too. Someone's already done that conversion. Whichever way you want to do is fine. Just make sure that you write all of the units out, McKenna, and make sure that you know what units you're using to make sure that everything goes smoothly. Okay, so we know pi. What else do we know? We know the temperature. What's the temperature? So it is 278.15 Kelvin. What else do we know? Thomas? Can we find molarity? How do we find molarity? So is that 21.5 grams of water? 21.5 milligrams of water, or what is that? This is hemoglobin. Can we find molarity with what we have so far? No. Not directly, not this way. How did you find it, Brianna?
You convert milligrams to grams, and you convert the 1.5 milliliters of solution into liters. That's
so we can do mass per volume, but that's not molarity. Chase?
They gave you what either ones it could be, so I was doing a process of elimination where you do both to see if you get the pressure.
What do you mean you did both?
You just take one of them and then
One of what?
one of A or B, the molar mass, and then I multiply it by 1,000 grams per mole, so it's 63,350, and then I just do the equation twice to see which one you do.
Okay, so that could work. We could do process of elimination. We could trial and error. We could try both of the molar masses, find the number of moles. Now with that number of moles per volume, We can find the molarity and try each of them and see which one matches up with that osmotic pressure. What's the other way you could do it, Shane? Is it? Anyone do it another way?
Can you use the density of water?
Well, we could use the density of water, but we don't know how many moles, so it doesn't really help us out. Taylor? So we're not going to do density because it's not 21.5 milligrams. That's only the solute. You can't use solute to find moles. What else do we know? There's one other thing that we know. Chelsea? So we know the pressure. There's one other thing. What constant? 0.0821 liter atmosphere per mole Kelvin. Gas constant. So one more thing we know. Alex?
Well, you don't know the amount of liters from molarity.
Okay, great. So we know part of molarity. We know the volume, but we don't know the number of moles. This is what we're trying to get to. So what were we saying, Shane? We also know the Van Hoff factor. What's the Van Hoff factor for any protein? What's the assumption? 1. So if we look at all this stuff we know, what's the only thing that we don't know and hence can calculate? If you know the molarity, you know the mass, and you know the volume, can you guys find the molar mass? Figure it out. From this, calculate the molarity. Once you have the molarity, see what you have in order to solve the molar mass. And by the way, doing trial and error is not wrong. I just want you to try doing it both ways.
Okay, so this is wrong then.
So this is atmospheres, and this is no units. I'm assuming that's liter atmosphere per mole Kelvin.
I just don't have enough room right now to write it. I have enough here. I'm just like trying to finish. I'm trying to
So
finish.
what are you solving for
We
here?
were gonna solve for molarity.
Okay, great. Solve for molarity.
We
And then
did
try to
that.
figure out with what you have if you can back out the molar mass.
Okay.
Do we have to convert? Like that, this is throwing off like torr and kilojoules. Do we have to convert, or do you? Because like in one of the homework problems it said bar, like millibars, and then bars. So like I'm just getting confused by all
Yeah,
the
so you
different
always
pressures.
have to make sure that you use the same units. So torr is not a measurement of mass, though, or molar mass. Torr is a measurement of pressure.
You know, that's what I'm
So
saying.
you have to
like,
go from torr to whatever units you have here. What units do you have here that you haven't written?
You stick it in the middle of our
Isn't that more No.
Okay, so give me 1 second. So guys, we have 2 minutes left in class, and I wanted to set you off in the right direction. So I think, and let me see if this is the right one. Yeah, so for osmotic pressure, what I wanted to try to get at, maybe it's easier to do this. Let's do this. What did you guys find for molarity for that last problem?
2.0800
Times 10 to the negative 4th moles of solute per liter of solution. You guys good with that?
Yeah, then you divide.
So then how do we find molar mass from this? We know that molar mass, molecular weight, is grams of solute per mole of solute. So how do we figure out those units from molarity? How many grams of solute do we have? How do we know how many moles we have? This molarity was from what solution? How big was this solution?
So you divide by 0.150.
So big picture. I want everyone to pause and stop looking at their paper. Concentration is the ratio of solute to solution. Doesn't matter how much or how little you have. We had a small amount, 1.5 milliliters. That ratio is going to be true. So you can do proportions if you want and figure out, well, how many moles were there in 1.5 liters? Or you can set it up like I did. Instead, if you have 1.5 liters of solution, you can do a unit conversion problem using this as your your conversion factor. How many moles is in 1.5 milliliters? Did anyone figure that out? If we have this concentration of solute in molarity, and this is how much volume we have, how many moles are contained within that? Tatiana? 3.125. Sorry, times what? And that's exactly what we needed on the bottom here. 3.12 times 10 to the negative 7th moles of solute. What is that ratio? Did anyone find that ratio? In the purple square? Anybody? 60 what? Anybody? Help me out. Somebody. Tatiana? 68,009. Or 68.9 kilodaltons. Was that even one of our options? No. Okay, so the answer C is correct. All right, so class is over. We have our exam next week. There's a lot more of these on the slide, so work through a few more examples. Make sure you guys can do this. Have a good weekend. What was your question?
Was that November 8th?
November 8th is the presidential election. Make sure you go out and vote.